Yeah, so I want to continue our discussion on risk-aware bandits. So last talk, we talked about best arm identification in the fixed confidence setting. And the talk before last, we talked about best arm identification in the fixed budget setting. So today I want to switch gears a little and talk about some stuff that is very recent. It's going to be presented at ICML in the next couple of weeks. That is neither fixed confidence nor fixed budget because we are interested in the regret minimization setting. And here we can choose more than one item at each point in time. So this title consists of many big words, which I'll try to explain during the course of the talk. Say it is titled Probably Anytime Safe Stochastic Combinatorial Semi-Bandits. Combinatorial because we can select more than one item at each time. And this is joint work with two of my students who did most of the hard work, and I'm only the communicator. Right, so let's get started. All right, so this is an outline of the talk. I will not read through all of this. But you know, the flavor of the talk is roughly the same. I will tell you what's the problem. I will tell you what is the result. I will then tell you what is the algorithm, and I'll tell you what. Okay, I'll tell you about lower bounds. So every algorithm must satisfy certain lower bounds, right? Then I'll provide you with details about the algorithm before I sketch some interesting elements of the proof of the upper bounds and the lower bound. All right, so everything I hope will be easily understandable by students here. Let me know if you have any questions, all right? Okay, so motivation. So let's start off with the motivation of our work, right? So we have a certain web page in which we can only display a small number of advertisements. Perhaps our web page is not very big. We can only display up to 2 advertisements, one from each company, one from a fast food company and one from a soft drink company, all right? Because our web page is not very big. So there are possibly many options out there for us to put on our web page so that it maximizes the click-through rate of at least one of the items, but we can only put 2 items, say, one from group A and one from group B, all right? So, is this working? Something is stuck. So we are going too fast. There's a delay between this and that. There's a technical. All right, so there's now the delay is past. So the permissible candidates are one item from the first set and another item from the second set. All right, so I'm going to choose one item from the first set and one item from the second set. And in our work, we can choose, we are permitted to choose strictly less than 2 items, strictly less than k items in general. All right, so, but say for the sake of argument that we're going to choose 2, for example, we select ST, which consists of 2 elements, one from the A set and one from the B set. And we're going to observe whether or not it is clicked, whether or not AT is clicked or whether or not BT is clicked. And whether or not either of these is clicked depends on a certain unknown probability distribution, which in my works are denoted by nu. Okay, so this is the setting. Here we basically want to select subsets of a ground set, not too large, and we can observe the feedback from each of the elements or each of the items that we select, all right? Okay, let's hope this works. All right, so there is a certain Oracle best set, which is the set, for example, McDonald's and Coca-Cola here. And what do we measure our algorithm against? Of course, you have already heard about regret, but in our setting, the regret is defined in a slightly different, in a slightly involved manner, which I'll walk you through, okay? So we're going to minimize the cumulative regret over T time slots. T is fixed. You can think of this as fixed budget. And we are measuring against an oracle who knows which is the best subset. And here the best subset is McDonald's and Coca-Cola. And so the best subset will yield this amount of reward. But this is a random variable, so we had better take the expectation to get a number. All right, so that is the oracle's reward across T time steps, the first term here. Now, you're going to play this game in a sequential manner, and you're going to select a sequence of subsets as T. And each time you're going to get on expectation, expected value of the sum of items in ST of their unknown, of the random variable that is realized. Okay, and these follow some unknown distribution. So you want to make this quantity as small as possible, and this whole work is going to quantify how big or how small this is under a special risk constraint. Okay. All right, so this is more motivation that we will go through quickly. So here, the motivation is really in advertising, all right? We want high click-through rates, but we possibly want a consistency, low fluctuation of the rewards. Another example that I think it could be applicable, but it's not immediately, fitting in our model is transportation. So here, I have already alluded to this yesterday, but here there are two hubs, all right, that represent two different items, one from subset A, one from subset B. For example, you want to commute from your house to your office, and you certainly have to pass through this point, maybe to drop off your wife or your husband, all right? So you definitely have to stop here, okay? So you are going to have to experience two hops. But there are many choices that you can choose to get from your house to your spouse's office, and from your spouse's office to your office. All right, and you want some consistency, some less variation. And here, just like in the previous talk, we're going to measure variation or risk via variance, but you can do it in any way you want, okay? So consistency, low variation of the total travel time, right? So we want high reward, which means high mean. In this case, actually what we want is low travel time on average. And we want a consistent reward, which means low total variance. That's the way we are going to measure variation in this talk. But as I alluded to yesterday, if you have appropriate concentration bounds, you can replace this word variance with anything that you like. Okay. Right. So this will form our risk and safeness constraint in what follows. All right. Yes. No question is stupid. Huh? Because there could, okay, so you could, why are we taking them together? Because we can select subsets at each point in time. And those subsets need not be, this is just a schematic. You need not select, say you have K hops, you need not select K different paths, K different edges of this graph. You could select less in our model. As I alluded to, in the advertisement example, you have a certain web page that is like this big here. You can place 10 ads, you could place 2 ads, all right? And initially you might want to place fewer ads. So, you cannot do things independently, as we will see. All right, so there are several risk-aware formulations which I'll just flash out here. So you could minimize the cumulative mean variance measure. I've already alluded to this yesterday. And there are some works that allow for some safeness constraints to be violated at a few times, sublinear times. For example, t to the 3/4 and log t. There's a line of work known as conservative bandits, in which you must gain a certain fraction of the reward. There are works that encode certain constraints in terms of a knapsack constraint. And what is most closely related to our work is the following, where the reward is in a certain can be expressed as a certain linear function of some unknown parameter theta star. And you want these rewards at each point in time to be at least a certain fraction of a base reward with high probability. We'll see that this is somewhat similar to our constraint, which I have not told you about. Okay, so let me now define a certain instance of our problem. Okay, an instance of our problem will be defined by 4 objects. These 4 objects, the first of which is a ground set of L items. L is a large number of items. Okay, so those are all the fast food restaurants and all the soft drinks and all the unhealthy food that you can think of. All right, but on a web page we can only display a certain number up to K web pages or up to K ads on our web page, and that is encoded in this set of subsets AK. Now let me walk you through this. So this set of subsets is consists of sets in the power set 2 to the e, such that the size of each subset is not more than K. So this is a collection of subsets of the ground set with cardinality at most K. And all subsets of a legitimate set in AK must remain in AK. So every subset of a legitimate set AK must be in AK. All right. So that is basically the structure of AK. Now, each item is associated to an unknown distribution, which I've already alluded to, nu I, and all these are sigma squared sub-Gaussian distributions. You can think of sigma squared as a large number here, all right? Because not all of them have variances sigma squared. All of them will have variances like sigma I squared, they are unknown, and these quantities are smaller than sigma, okay? So the means and the variances are unknown, the bound on the sub-Gaussian is known, okay? So here, just like in the previous work, we have an upper bound on the permissible variance, upper bound on the variance, and this is a certain threshold that is set and is known by the user. Okay, so these elements consist of an instance. So we have a ground set, we have a collection of subsets, we have a collection of L distributions with unknown variances, and we have a permissible bound on the variance. So at every point in time, we are going to select subsets instead of just selecting one item. And how do we measure the quality of a certain subset? All right, there are two different measures, two different statistics of a certain subset, or what we call a solution. All right, so first is the reward, the expected reward. It's basically the sum of the expected rewards in each item. And I forgot to mention that all the rewards here are positive for this to make sense. All right, so your rewards have to be positive. Now, if you select more items and you put them on your web page, if you select more advertisements to put on your web page, the chance that one of them is going to be, malicious or harmful is also going to increase. So we're going to model this by saying that the risk of a particular solution is the sum of the risk of the individual solutions. Okay, so here we have again, like in the work I talk about, and so this is a continuation. All right, we can partition all possible admissible subsets into a few families. All right, so we have a safe set. We have the safe set, which is a set of all subsets whose total variance is smaller than the permissible upper bound. We have the optimal safe solution, which we assume is unique. That is the solution that maximizes the mean subject to the fact that it is safe, in the sense that its total variance is less than the permissible upper bound. We have the suboptimal set. The suboptimal set is a set of all possible solutions here, bottom half, all right, whose means are smaller than that of the mean of the optimal safe solution. We have the risky set. There's all this stuff on top here, whose expected reward is bigger than that of the optimal safe solution. Okay, so again, the x-axis is the variance, the y-axis is the expectation. All the subsets live in this space here. We have indicated a few subsets. There is a certain critical line here called the permissible upper bound on the variance. To the right of all this, to the right of the permissible upper bound on the variance are subsets that are unsafe. To the left, we have the safe sets. And among the safe sets, we have one distinguished set that is the optimal safe solution. There are some risky solutions, and there are some suboptimal solutions. Okay, so there's a partition here. All right, and again, we have the mean gap and the variance gap of individual solutions, S. Okay, I think I don't have to talk about this if you were at my talk yesterday. Mean gap and variance gap characterize the difficulty of the problem. Okay, so we can partition all subsets in AK, the set of all admissible subsets, into this in this picture here. All right, so if you can only remember one thing from my talk, this is the thing that you should remember. So I've already talked about the regret that we want to minimize. We want to find a policy that minimizes the regret. This is the same expression that I flashed down here a few slides ago. But what we want to do is to make sure that this interesting constraint holds. What is this constraint? This constraint says that at every point in time, the subset that you select ought to be in the safe set, and this must hold true for all time with probability at least 99%. Okay? So at every point in time, you need to make sure that what you select has a bound on the variance that is not too large. So intuitively, how do we ensure that this is the case? Right? How do we ensure that this is the case? Can you, at the very beginning, select a subset with many items? variances are non-negative. So if you select a subset with many items, say you're allowed to select subsets of size up to k. You select k items. You're super greedy at the start. You might very well bust the budget. So the algorithm that we are going to suggest goes as follows. We're going to be very conservative at the very beginning. We're going to probably select subsets of size 1 or 2. All right? Until we are very safe, we are very sure of the variances of each of the arms of the items in order to ensure that this constraint holds true. So one more time, at the very beginning, we are going to be conservative and select subsets that are small. And then we will grow the subsets in size over time, such that we accumulate accumulate reward over time, and yet ensure that this probably anytime safe constraint holds. All right, we are also going to consider sequences of problems because my background is information theory. We do asymptotics. Okay, so we are going to consider this class of sequences of algorithms that are called delta T variance constraint consistent algorithms. All right, what this says is that the regret satisfies little o t to the b for all b bigger than 0. So roughly speaking, if the regret is like logarithmic, you satisfy this condition. And you have this delta t sequence here comes into play in this condition here. What we want is that this constraint holds true with higher and higher probability as time goes on. By the way, I forgot to say that this sequence here is little o1, goes to 0. All right, so we want the constraint to be more and more stringent as time goes on. Okay, so I already, yes?
So about your anytime safety constraint, suppose there is one item whose variance is above your safety.
So we assume that all the variances of the individual items must be smaller than the, this must be true for all items I in L. Okay, otherwise it doesn't make sense. Okay, so I'm going to write a few things here. All right, but the next thing I want to talk about is what we cannot do. As information theorists, we are interested in converse results. So this sentence here is a little bit hard to parse, so just listen to me. All right. So if we have a sequence, all right, that scales in this particular fashion for some b, then for any instance, the regret of any algorithm is lower bounded by this. But it's really hard to understand. So let me try to parse this for you. Let's just take b equals to 1. And then suppose we have sequences that look like this, equals to c times t. All right. So the exponent is linear, which means that delta t is like roughly exponentially decaying with time. Okay. So what this means is that here in your constraint, you want this probability to go to 1 exponentially fast. You are very greedy. Okay. So what this impossibility result says is that the regret of any algorithm is going to be omega t to the 1 linear. All right. So if you are too demanding, all right, you want to converge to 1 too quickly, then there is no hope to get any sublinear algorithm. Okay. So the intuition is just some simple checking. Okay. To check the safeness of a particular solution, you need this number of samples. And if you replace this log 1 over delta t by this linear term here, you see that you will incur a regret that is linear. Okay, so in the following, we will only consider the case in which delta t, which is this sequence here, satisfies this constraint for all b bigger than 0. This is again very difficult to parse. So we're going to take delta t's, all right, to be roughly t to the minus lambda, polynomially decaying, lambda bigger than 0. We cannot take delta t's to be exponential for this converse reason. All right, so this is the regime that we'll be interested in. Let us denote any algorithm that achieves the asymptotic minimax lower bound as follows. So let me pass this expression. The regret is a function of the algorithm you use, the time horizon, as well as the instance. So let's look at the worst case instance. Let's look at the worst case regret over all possible instances. And let's look at the best possible algorithm. Okay, so this is some good algorithm that we would like to understand its properties. Okay, so this is a bit hard to understand. So let me just walk you through some of the key elements of this expression here. So we are going to take sequences that converge to 1 as follows, all right? Sequences that converge to 0, I'm sorry. So polynomially decaying. And we have a upper bound and a lower bound and embedded in this particular statement here. So the lower bound says that the regret of the best possible algorithm must scale in this particular way. There exists, in addition, there exists an algorithm whose regret scales in this particular way. All right. Now let's just focus on the first term here. These two terms are the same, up to k. All right. So it involves the minimum safe suboptimal gap of item I. So let's look at item I, and let's look at all subsets that include item I that are safe and suboptimal. All right, so that is a measure of the difficulty of ascertaining the suboptimality of this particular subset of item I. All right, so that appears in both the upper and lower bounds. So here there is another term that involves some hardness parameter that I will not write down because it's too complicated here. So this is just a hardness parameter that is a function of some gaps as well as an instance. But the term that scales in logarithmic in T is the first one. Okay, so that is a problem-dependent bound because it involves these gaps. And here in addition, in our work, we also have a problem-independent bound. It's a problem-independent bound in quotes because we need the variance gaps to be lower bounded by some delta V here. If the variance gaps are not lower bounded, then the regret is vacuous. Right, so here there are some interesting elements that I would like to highlight that are easy to parse. All right, so the first term here, square root KLT, the upper bound and the lower bound just differ by a term that is logarithmic in T. So this term here in red is due to ascertaining suboptimality of suboptimal solutions. So this term matches up to square root log T. All right, this additional term here is due to safeness checking. So remember that we have some safe solutions and some unsafe solutions. In order to ascertain that a solution is safe or unsafe, we need to check it a few times. And this is the worst case number of checks that we need. Okay, this K squared here can probably be improved. All right, so there are two terms, two contributions, one due to suboptimality and one due to safeness checking. And you will see that these two factors will appear time and time again in our talk. Yes, 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 yes. So the total number of items is L. The total number of items you can display on a web page is at most K. All right. Why is it K into L? L choose K, you mean?
L choose K.
Yeah, so this is better than L choose K because L choose K is very large, right, compared to K times L. Yeah. Okay, so there is a... No, we are not. If you take correlation into account, you can probably shave off 1K here. Yeah, yeah. So you can shave off 1K. You can shave off 1K here if you take correlations of the items into account. Yeah, so that is even more favorable. Yes, that's right. But if there is correlation among the arms, among the random variables Wi, then you can do a little bit better here. Yeah. Yeah, you don't throw two completely different things, right? Like, yeah, one item that is suitable for men, one item that is suitable for women. That might not be favorable. Okay, so there is an algorithm that does this, and I want to highlight some key interesting elements of this algorithm and some analysis of it. Okay, this algorithm is actually very simple, okay? We start off with a particular instance that we do not know the distribution. We start off with the horizon that we do know, and we start off with a confidence parameter, delta between 0 and 1. This algorithm proceeds in phases, and the phase counter is called P. Within each phase, there are different time steps, and so there's a time step counter as well. The warm-up phase is quite trivial, so we omit discussing it. So we will adopt this optimism in the face of uncertainty principle in line 5 here, all right? So in line 5 here, what we are going to do is we're going to identify, but not pool yet, a solution that maximizes the upper confidence bound on the means of this potential solution A. So here we maximize upper, U stands for upper confidence bound on the mean, but we don't maximize over all possible subsets A. We maximize this over only those subsets that are possibly feasible or possibly safe. How do we define possibly safe? Lower confidence bound on the variance should be smaller than the permissible threshold. So that is the first step, identify, just identify. But this may be dangerous, all right? Because this guy here, AP, may contain too many items. As I said, at the very beginning, you shouldn't display all K ads at once, even though the budget is K. So we are going to invoke another subroutine, which I will describe to you using pictures later on, but here using math, called greedy split. To split this solution AP, and these sub-solutions should be with high probability safe. And the way we ensure this is through upper confidence bound on the variance. Okay, so I'm going to show you the procedure using pictures later on. Then we are going to pool now these sub-solutions. Remember, for every solution, every subset of it is also a solution. That's why we can do this. All right, so we're going to choose or pool these solutions and update the statistics and update the empirical sets and update the counters, so and so. So we update the phase counter and we update the time step counter. All right, so within each phase, there could be many time steps, a total of NP time steps, because the solution AP is split into NP sub-solutions. All right, picture time. So this is easier to understand. So this is a solution that we first identify by means of the optimism in the face of uncertainty principle, which means we maximize upper confidence bound. All right. Then we look at this solution here, and we look at the permissible upper bound on the threshold. A very natural thing to do when you bust the threshold is to split this solution that you have identified into sub-solutions, each of which is maximal, in the sense that I1, you try to put it in here, you see whether it's upper confidence bound, busted the permissible upper bound of variance. No, because we can still add I2 to this stack here. All right, and why do we want to add I2 to this stack? Because if I pull AP1, okay, its expected reward will be bigger than if it only has one item. I should be as greedy as possible. Now, can I be very greedy and put I3 here? No, because I will bust the budget. All right, so I have to create a new sub-solution, I3. Okay, can I put I4? No, because it will bust the budget. At least that's what the intention is. All right, now then I have to create a new stack or a new sub-solution AP3, which will then contain these two sub-solutions, which will then contain these two ground items here. So I start off with a solution and I do this greedy splitting. And what I'm going to pool is in fact AP1, AP2, and AP3. So the total number of sub-solutions here is 3, which is actually a random variable. Okay, so what I've just said is we're going to split the solution according to its upper bound of variances to be ultra safe. And you can see that, okay, if you had just pulled this solution, you're going to incur this little bit of regret. That is the expected reward of the best possible solution. That's mu star. That is the expected reward of this particular identified solution AP. You're just going to incur this small little slice of regret. But now you're going to incur much more because you have split the solution into some smaller solutions. And you're going to incur these 3 white bars of regret. 3 white bars. And through some simple algebra, you can quantify what these 3 white bars are. That is the original regret plus mu star is this quantity here, multiplied by the number of sub-solutions you have created minus 1. So that's simple algebra. Okay? So you have actually created more regret due to this splitting. Yes? Very good question. Well, this is arbitrary. You can actually optimize this as well in order to create less or fewer sub-solutions, but that's something we did not do. Okay? So this is a very simple equation that we make use of, and I've already explained where this comes from through this picture. All right, so at any phase P, we can actually show that the number of sub-solutions that we get is not more than this quantity that depends only on the instance which we call Q. All right, this is not so important, you don't need to remember this. But the message of this lemma says that the total number of sub-solutions that we get if the upper confidence bound lies in a certain slice can be sandwiched within two bounds, one lower bound and one upper bound, that only differ by a factor of 2. So the punchline here is that greedy splits yields at most 2m sub-solutions. M is this slice of the upper confidence bound. And we can actually show that because the upper confidence bound is lower bounded by this m-1 times the permissible upper bound of variance, any splitting algorithm will yield at least m sub-solutions. So this is quite tight, right? And doesn't result in that much of a loss. I want to show you now the accumulation of regret as time goes on. This is a picture in which the x-axis is phase and the y-axis is instantaneous regret. And we have the red part and the yellow part or orange part, okay? At the very beginning, we have a lot of sub-solutions, we have a lot of subsets. And we are very uncertain about the safeness or safety of each of the subsets. So we incur a lot of red regret. The red regret are instantaneous regret due to safeness checking. Okay, and the red regret is always a factor of this mu star. Okay, so they are always of a constant length. Okay, see all these red bars here. At the very beginning, we are very unsure. So we accumulate a lot of instantaneous regret due to safeness checking and some instantaneous regret due to suboptimality. As time goes on, however, we are more and more certain of which subset is safe and which subset is not safe. And so the instantaneous regret due to safeness checking becomes less and less. And at the very end, we only accumulate instantaneous regret due to suboptimality. So that's how the analysis proceeds. That's at least the mind game that we play when we try to calculate the regret. Okay, at the beginning, we are unsure. So we have all these extra red parts. But really, the suboptimality is accumulated through the orange or yellow parts only. Okay, so there is some proof sketch here that maybe I'll go through quickly, right? So all these proofs go along the same lines. At the very beginning, we were conditioned on some good event. The good event is called E. Maybe we should call it G, right? So the good event is what we are going to spend time dissecting, all right? The bad event can be upper bounded by some term here that does not depend on the horizon. Fine. Okay, so now let's focus on the good event. Through a sequence of steps that I will not describe, the good event can actually be decomposed into two parts that have names. One is the regret due to suboptimality, and one is the regret due to safeness checking. These are called R suboptimality and R safeness checking, respectively. And I'll go into each of them. Now, for the suboptimality part, all right, this is a little bit technical, but you see that, all right, we will involve things like the gaps, all right? So these are the gaps associated to items I, all right, let me just show this, that are safe and suboptimal, all right? This part is similar to just standard combinatorial semi-bandits, if you know this line of work. There is an additional part that is due to checking of either suboptimality or unsafeness. So if we have subsets that are either suboptimal or unsafe, ascertaining either suffices. And hence we have this little factor here, C, whose denominator has a max. Because as long as I can ascertain that this subset is either suboptimal or unsafe, I can just throw it away from my consideration, and hence the denominator becomes smaller. Now this is the exciting part, all right? So this is safeness checking, all right? Safeness checking, there are some expression here that you don't need to pass, all right? Let me show you some picture here which you have seen before. This guides our analysis. So here what we need to do is to sum up all the red parts, right? Because those are the regret due to safeness checking. We need to sum up the red parts. Now, how do we sum up the red parts? How do we calculate area in calculus? We integrate. Now, there are two ways of integration. Do you agree? Riemann and Lebesgue. Okay? So Riemann would say, okay, let's just do this, count this. But this is too difficult for us to count. So what we do is we're going to look at how many people here, how many bars here have 5 mu star regret. Each one of these is mu star. All right, 1, 2, 3, 4, 5. How many of these bars have 5 mu star regret? And we're going to push them all to the front. And we're going to sum this in the Lebesgue way. We are basically going to create an upper bound that is easier for us to calculate. And this is exactly the upper bound on the regret due to safeness checking. This is what all this math is talking about. All right. So the Riemann way of summing here is too difficult for us. So we resort to this upper bound, which will allow us to sum in a very convenient way the safeness part. That will expose the hardness parameter. Okay, I know I have not provided any details, but at least I've provided some idea about how we do this in a systematic way. There are 2 ways of summing. Okay, so there is a suboptimality due, there is a regret due to suboptimality and the regret due to safeness checking. And I hopefully have illustrated how to calculate some of these elements. Okay, so yeah, fine. All right. So we also have a converse, or converse means impossibility result. How do we establish impossibility results? We establish impossibility results by coming up with instances that are hard. And here, let us consider a k-path semi-bandit problem, because here we are allowed to choose k items at each point in time. So here we have a directed graph from the start to the end, and each path here consists of k directed edges, arcs. So we have a bunch of paths, we have L of them. And this L is parameterized as 3L1 plus 1. L1 is carefully chosen. And I'm not going to say how we choose it. Now, this set of paths here is going to be partitioned into 4 parts. All right, 4 natural parts, as in my diagram with 4 quadrants. There is one path that is the optimal safe path P1. All right, this path is optimal safe. There are L1 carefully chosen safe and suboptimal paths. There are L1 risky paths. All right, so they are unsafe, but possibly have means that are bigger than the optimal safe path. There are L1 unsafe and suboptimal paths. And each one of them here is going to be carefully, each one of the paths here is going to be carefully constructed so that we have an instance-dependent lower bound. That makes sense. And I'm just going to talk about, maybe one of them here. All right. So here, let us just say that, each item in the first path has mean P1. Okay. And how do we do this calculation here? All right. For the optimal safe path P1, we need to check that it is indeed safe. And in order to check that it's indeed safe, some simple statistics will tell you that you need this number of pools. You cannot avoid this number of pools. Okay? Why? Here the denominator is epsilon v. What is epsilon v? Epsilon v is the distance between P1 here and the wall or the boundary here. So this gap here will appear as square denominator, as a square in the denominator. So you will incur this much regret because each of the arcs has a certain regret associated to it of delta. So we do this systematically for each one of the quadrants that we have constructed, put everything together, and that actually gives you the lower bound. So here, for example, we have something that is suboptimal. To assert that something that is suboptimal, we need this number of arm pools, which is the mean gap squared in the bottom here. All right, and there are many other analyses which I will not go through here. Okay, we put everything together. So I've gone through, what have I gone through? The problem formulation. I have gone through a result, or maybe 2 results. I have given you our algorithm, which involves greedy splitting. I have hopefully gone through some interesting analysis of how we do simple summing in different ways. I have gone through some ideas of construction of lower bounds in this combinatorial semi-bandit setting. And now I want to finally end off by showing you, yes,
So in your algorithm, you first identify a solution, right?
Yes,
Does
AP.
it involve solving an abstract problem?
No, it just involves, let me show you, okay? It just involves the following. Identify a solution. What is the meaning of it? All right, let me just go, maybe I went through this a little bit fast, but since we have time, we can discuss. So how do we identify a solution? This means upper confidence bound on the mean of the solutions, of the solution A. The upper confidence bound of a solution A is basically the sum of the upper confidence bounds of each one of the items within a solution A. All right, so that's a number. We're going to maximize that over all possible subsets that are currently admissible. What is the meaning of currently admissible? Currently admissible basically means this should be Cal S and this should be Cal S, right? So currently admissible basically means that they are possibly safe. Possibly safe means that lower confidence bound on the variance should be less than sigma bar squared.
So this is essentially knapsack.
I'm not so familiar with the knapsack literature, but yeah, this is upper confidence bound. It's constrained.
Say that, solving this problem, let's say the use and the else are given now.
Yes.
Then solving this problem is.
Yeah, but if you have like small subsets, it's okay. Yeah.
Okay.
Yeah, K is not so big.
Okay.
Yeah. So that hopefully that answers your questions. Any more questions? Because our experiments are not so critical. Let me just do this to move faster to the experimental part. But the experiments are quite meaningful, okay? Let me show you. So what is our baseline when we do this experiment? All right. The baseline is, of course, the unconstrained case, combinatorial semi-bandits, all right, without any variance constraint or anything fancy like that. So we want to quantify, we want to empirically quantify the additional regret due to safeness checking. And to see that our algorithm actually degenerates or particularizes to the unconstrained algorithm, okay, if there are no constraints. Okay, so in this particular setting, with all these numbers, can you tell me what is the optimal set? Optimal safe set. All right, actually I have the answer there. All right, but let's look at the numbers here. The means are as follows. All right, they are in decreasing order, and the variances are as follows. And the upper bound is sigma bar squared equals to 0.6. No matter how you add three numbers here in the variance, you will not exceed 0.6. So it's essentially unconstrained, but the algorithm does not know it. Okay, I think the variance here is 0.52 if you add these three numbers. Okay, and this is the optimal set 1, 2, 3 because it has the highest mean and yet its variance has not busted the constraint. Cool. So this is basically our algorithm without constraints. And we compare to COMP-UCB1, which is a standard combinatorial semi-bandit algorithm. And I just want to show you this picture here. The x-axis is the time horizon, and the y-axis is the cumulative reward. So one of these lines is the combinatorial UCB1 here. Okay, so here the higher the better. We are not plotting regret, we are plotting reward. The higher the better. Combinatorial UCB1 goes as follows, right? This is the combinatorial UCB1. And our algorithm goes as follows. All right, our algorithm picks up less reward. Why does it pick up less reward? Because at the very beginning, it does a lot of safeness checking. It has to ascertain that the unsafe solutions are indeed unsafe, but there are no unsafe solutions, all right? So it has to do something at the very beginning to ascertain that everybody is safe. So that is the amount of time that it takes. Then, after this burn-in phase, the slopes are the same. So we recover combinatorial UCB1 here. All right, so it seems that, okay, this is a sanity check. Okay, fine. All right, I'm not going to go through this experiment here, which just says that we can do the job with high probability, okay? But one thing that I did not talk about, which is also quite interesting, is how the hardness parameter depends on the gaps. And in some cases, the hardness parameter, in some regimes, the hardness parameter depends on the gaps as the inverse of the square of the variance gaps. I think I also alluded to this in my previous talk. So here what I'm going to do is I'm going to change the threshold on the risk of variance within a certain interval. And then I'm going to check whether the additional regret due to safeness checking depends on the hardness parameter as our theory predicts. Okay? So what we should see is a straight line if we plot the additional regret due to safeness checking against hardness parameter. All right, so okay, the hardness parameter scales as 1 over the reciprocal of the square of the gaps, variance gaps. And the blue dots are our experiments. and we have a line fit here, which looks reasonable. All right, so here, this is an empirical experiment to say that, okay, our analysis looks okay, it looks tight in the dependence on the gaps, as it should. All right, perfect timing. So this work actually formulates an anytime safe, that should be N, anytime safe combinatorial semi-bandits problem. It proposes an algorithm based on splitting techniques. We provide problem-dependent and problem-independent upper and lower bounds. And the algorithm can be quite interesting, all right? It uses some splitting ideas and some clever, not clever, we shouldn't be praising ourselves. Some alternative summing techniques, all right, to calculate in a convenient way the regret. We designed some experiments to corroborate our theoretical results and to illustrate the empirical performance. There's no benchmark, nothing to compare against, to the best of our knowledge. So we can try to close the gap in the bounds with an, okay, so this comes to a Prashant's question. We have no correlation assumptions. It will be nice to understand if there exists some correlation assumptions among the items, whether that allows us to close gaps or not. Yeah, but if the items themselves have some get like linear bandits, maybe there is some hope of getting tighter bounds. So we can consider other safety issues, but the main point here, as I mentioned, if you can only remember one thing, is that we take the probability over all possible time that the subset we select must be safe with probability at least 1 minus delta. Okay, that is the interesting part of this whole work. All right, so this is a different formulation, okay, and we have some algorithm that may spark future work. All right, thank you very much for your kind attention.